This video is meant as a review of our exponential functions unit. One thing we want to be able to do is to differentiate between linear, quadratic, or exponential functions. So based off of a table of values, we can figure out if we're dealing with a linear, quadratic, or exponential function. Start by checking the first differences. If the first differences are constant, then you know this is modeling a linear function. If the first differences are not constant, then it's not a linear function. Next, try the second differences. If the second differences are constant, then this is a quadratic function. If the second differences are not constant, then it's not quadratic. So check the ratios between your first differences. If the ratios are constant, then this is an exponential function. So just to reiterate, if you have a table of values and you're to determine if it's a linear, quadratic, or exponential function, check the first differences, second differences, or the ratios between your first differences to decide whether you're dealing with a linear, quadratic, or exponential function. Another thing we talked about in this unit was how to work with exponents. We have different exponent rules for simplifying expressions that have powers. If you're multiplying powers with the same base, or dividing powers with the same base, or you have a power of a power, or a zero exponent, or a negative exponent, or a rational exponent, how do you work with these? Well, if you're multiplying powers with the same base, add the exponents. 5 and minus 3 is 2, so this simplifies to 2 to the exponent 2. And if you're dividing powers with the same base, you subtract the exponents. So 5 subtract minus 3 is 8, so this is 2 to the exponent 8 when you simplify it. I'll say that again, 5 minus minus 3. It's that double minus, that's the same as 5 plus 3. When you have a power of a power, multiply the exponents. So 2 times negative 3 is negative 6. When 0 is your exponent, the answer is always 1. And now I want to talk about negative exponents. Here's a power with a negative exponent. I also have a power with a negative exponent up here. I can simplify that further. Remember, you can rewrite the power with a positive exponent if you make the base the reciprocal. So the reciprocal of the base with a positive exponent is how you can simplify this. I do the same thing up here. The reciprocal of 2 is 1 over 2, and the exponent is now positive. So this gets you the same result. But now I have a positive exponent. And over here, we have a rational exponent, which means the exponent is a fraction. And we can rewrite that as a radical. The denominator of the exponent is what root you're taking. If it's a 3, it's the cubed root of 216, and the numerator of your exponent is what exponent you're raising that root to, that radical. So we've simplified our expressions, and now we can actually evaluate, because once you have a positive exponent, you can think of that as expanded form, like 2 to the exponent 2 is 2 times itself. 2 to the exponent 8 is 2 times itself 8 times. 1 over 2 to the exponent 6 is 1 over 2 multiplied by itself 6 times. Anyway, if you have a positive exponent, you can actually work out what the expression is equal to. 2 squared is 4. 2 to the exponent 8 is 256. A half to the exponent 6, well, we can split that up. 1 to the exponent 6 is 1. 2 to the exponent 6 is 64. So a half to the exponent 6 is 1/64. 2/3 to the exponent negative 2 is 3 over 2 to the exponent 2. 3 squared is 9. 2 squared is 4. So it's all equal to 9 over 4. The cubed root of 216 is 6, because 6 cubed is 216. So if I want the cubed root of 216 squared, it's 6 squared, which is 36. So this was just a recap of the exponent rules that we talked about in this unit. Now we can use our exponent rules to simplify expressions like this. Remember, if you have an exponent on brackets, every part of the term in the brackets has that exponent. So the 27 is to the exponent 1/3. The a to the -3 is also to the exponent 1/3. b to the 12 has the exponent 1/3. And when we have a power of a power, we multiply the exponents. So that's why I'm multiplying -3 and 1/3. 12 times 1/3. I do the same thing down here. The exponent of 1/2 applies to each part inside the brackets. And you'll see I've indicated that here. Now, 27 to the exponent 1/3 is the cubed root of 27, which is 3. 16 to the exponent 1/2 is the square root of 16, which is 4. -3 times 1/3 is -1. 12 times 1/3 is 4. -8 times 1/2 is -4. And 12 times 1/2 is 6. So I simplify the numerator and I simplify the denominator. Now I can keep simplifying this expression because I'm dividing powers with the same base. 3 divided by 4 is 3/4. A to the -1 divided by a to the -4 is a to the -1 minus -4. B to the 4 divided by b to the 6 is b to the 4 minus 6. Remember, when you're dividing powers with the same base, you subtract the exponents. So when I do that, I end up with this. 3/4 times a to the 3 times b to the -2. And I can clean this up and write it as a fraction. Remember, if you have a negative exponent, that means this power has a positive exponent in the denominator of the fraction. So I can simplify this to look like this. 3a to the 3 divided by 4 times b squared. I took this complex looking expression and I used my exponent rules to simplify it down to a simpler expression. Now we also talked about how to turn an equation into a graph. We use the parent function and analyze the transformations of that parent function to make our graph. So first, the parent function. In my function, the base of the power is 2, which means the parent function has the base of the power being 2. 2 to the x. That's the simplest function in this family. And I've drawn a graph of that here. I can figure out 3 points by just using 3 different values of x in this equation. When x is 0, 2 to the 0 is 1. When x is 1, 2 to the 1 is 2. So when x is 1, y is 2. And when x is -1, 2 to the -1 is 1/2 to the 1, which is 1/2, a half, 0.5. So I found 3 points on my curve, and I can just look through my function and find out what the transformations are and apply each of those transformations to each of these points. Okay, I have an a value of 0.5. It's positive, so there's no vertical reflection, but if I multiplied all my vertical values by 0.5, that would be a compression. So this is a vertical compression times 0.5. Here I have a k value of -2. That means I have a horizontal reflection. That's the negative part. And 2, I'm multiplying by not 2, 1/2. Just remember, you multiply by the reciprocal of your k value, not the k value itself. So because I'm multiplying my horizontal values by 1/2, that's a horizontal compression. They're going to get smaller. Translate left 4 and down 3. Those are my last 2 transformations. So now I'm going to make all of these transformations apply to each of these points on the graph. Now when I do that, I get points here. It might be tricky to finish off a nice graph of this, so just remember, we can also figure out where the asymptote of our graph is. Because we've translated down 3 units, the asymptote moves from the x-axis down 3 units. So we should draw the asymptote with a dotted line, label it with its equation, and now we can actually figure out where our function, f of x, is going to start leveling off. So then I can just draw a curve through my points, and there's the nice graph that I'm talking about. And once you've made a graph, you can more easily figure out what the domain and range of that function are. There's no restrictions on the values of x, but there is a restriction on y. Y must be greater than -3. You use your asymptote to help you figure out that. If it's on the positive side, y is going to be greater than -3. Just watch your symbol here. The direction actually matters. Make sure it says greater than, not less than, and don't put a line under it because it can't equal -3. So just to recap, when you're making a graph, start by drawing your parent function and a few points on it. Figure out by looking at your a, k, d, and c values what your transformations are, and then apply each transformation to each point you drew on your parent function. Once you have your new points, draw your asymptote so that you can figure out what the curve looks like. We can also come up with an equation of a function based on a description like this. An exponential function with a base of 2 has the following transformations: a reflection across the x-axis, a vertical compression of 1/8, a horizontal compression of 3/4, translated right 5 units and translated down 3 units. We're going to write an equation of the function and also the equation of the asymptote. Remember, this will be the format of the equation. B is the base of the power. We know the base is 2. So my equation is going to have a 2 here. I need to figure out what my a, k, d, and c values are based on the description here. And then once I figure that out, I can plop those numbers in and end up with an equation. Reflection across the x-axis. Well, the x-axis is horizontal, but if you're reflecting across a horizontal line, that means that you have a vertical reflection, which means our a value is negative. We also have a vertical compression of 1/8. So that means our a value is going to be 1/8. But remember, up here, I saw that a was negative. So it must be -1/8. That's my a value. That's what I put here. We have a horizontal compression of 3/4. Remember, if you're multiplying your horizontal values by 3/4, that means k is the reciprocal of that, 4/3. So k is 4/3, that's what I put here. We're translating right 5 units, so d is 5. And we're translating down 3 units, so c is -3. So this is the equation of my function. The equation of the asymptote, that's pretty easy to find. We've translated down 3 units. Look at the c value. That's what the equation of the asymptote is. So if you have a description of a function, just remember to think about what it means in terms of a, k, d, and c. In other words, take the transformations and turn them into your values that you see in the equation. Kind of the opposite of what you do when you're graphing. And the last thing we talked about in this unit was applications of these exponential functions. Now, we used a simplified model when we were making our equations. We just looked at what is the a value. The a value ends up being the initial value, or your y-intercept, for these simplified functions. B, the base of your power, is the growth or decay rate. Growth if your base is a number larger than 1, and decay if the base of your power is a number less than 1. So you need to read the question to determine which values you know. Usually from the question you can figure out what your initial value is, and you can figure out what your growth or decay rate is so that you can make an equation. And depending on what the question is asking, once you have an equation, substitute the known values into the equation and solve for the value you don't know. And in the previous lesson, we looked at how you can solve for y when you know what x is, but also how you can solve for x when you know what y is. So if you need a refresher on that, you can ask for some help. So in this unit, we looked at comparing linear, quadratic, or exponential functions. We looked at exponent rules involving power of a power, multiplying and dividing powers with the same base, zero exponents, negative exponents, and rational exponents, and how to simplify expressions. We looked at graphing exponential functions and making equations and solving application problems. If you need any help with any of that, just reach out and I will do my best to help.